This is a continuation of what we were doing before with the extreme value theorem. Just didn't have enough time to get through it then, but this is a really nice opportunity nonetheless to review. The reason why I mention the extreme value theorem is because the question is talking about find the absolute minimum and absolute maximum. So I know that I'm going to use the extreme value theorem. That is, if possible. So how do you know if it's possible to use the extreme value theorem? And we make that determination of whether or not f is continuous. And we make that determination not by studying the graph or looking at other things, but in this case by just knowing that sine and cosine functions, those are continuous, and for that matter differentiable. They're sinusoidal. So I've got sine squared, but that's sine times sine. Both of those are sine functions, so neither one is a problem. And I'm adding cosine to that. So we're good to go. So what does it mean to be good to go with the extreme value theorem? Well, what it means to be good to go is determine the largest and smallest function value. And when it comes to like why we care about doing something like that, well, I just want you to think about like in life, when you're talking to your friends about something, you talk about what's the best or the worst. You generally don't spend time on anything in between. You're like, let's talk about the most okay movies ever. That's what we're talking about. No, we don't talk about the best and worst movies or to whatever it is you're interested in. Let's say you're one of those League of Legends scrubs. You want to talk about the best and worst champions. You want to talk about the best players and the players who int all the time. That's what you want to talk about. You want to talk about everybody who's just like okay, which is what most people are, which is why they're all hard stuck in gold, because they're only okay. So that's kind of why we care about stuff like this. We're always interested in the most extreme, the mostest and the leastest. And I just want you to think about the pictures that you drew when we started out this quest. So we drew some things and asked you to draw different things that satisfied a continuous function that went from one point to another point. And one of the things you may have noticed is that sometimes the highest or lowest point is between the endpoints. Sometimes it is the endpoints, but other times it's between the endpoints. So this right here requires some more thought, but not a whole lot more thought, because we've actually talked about this already. This is talking about relative extreme values. So we can use the first derivative test. Actually, we're not going to use the first derivative test because the first derivative test does more than we need. We don't actually care if it's a relative minimum or maximum a whole lot. All we care about is where. So really, to get those values that aren't endpoints, so that we know what the highest and lowest point are, what we're going to look at is the critical values. So the endpoints, pretty straightforward. We want to evaluate f at 0 and evaluate f at 2 pi. Okay, so f of 0 is sine squared of x would be sine of 0 squared, so 0 squared, okay, plus so that's 1. F of 2 pi, sine of 2 pi is 0, 0 squared is 0, cosine of 2 pi is 1, okay. So those could be the relative min, I'm sorry, the absolute min or absolute max. They can't be, well, maybe they're both too, I guess that's true. But the other thing we need to think about is any interior points. And we do that with critical values. And what that means is we need to know when f prime of x equals 0 or f prime of x does not exist. And we know that this isn't going to happen here because of the type of function. It's sines and cosines. So that's not going to happen. Okay. But when is f prime of x equal to 0? Well, we should probably figure out what f prime of x is and then solve, huh? Okay, so sine squared of x, I'm using the chain rule. If you did not know to use the chain rule, yikes. So it's 2 sine of x, inside function is sine, derivative is cosine, minus the derivative of cosine, which is sine of x, equals 0. And I can solve this sucker with factoring. If you didn't know that, you should brush up on your solving equations skills. So when sine of x equals 0, x is 0, pi, 2 pi, right? That's what falls on the interval, right? 0 to 2 pi. And 2 cosine of x minus 1 means cosine of x is 1/2. So x is, let me check my trig hand. You can't see me, but that's what I'm doing. Cosine is 1/2, so I need pi over 3 in quadrant 1 and pi over 3 in quadrant 4 is 5 pi over 3. Okay, so the absolute maximum and absolute minimum for the function sine squared of x plus cosine of x, f of x, is going to be at 0, 2 pi, 0, I don't have to do 0 and 2 pi again, but pi, pi over 3, and 5 pi over 3. Now, I'm just going to simply substitute these into my calculator. So that's where I got my values from, in case you're curious. So when x is pi, I got -1. When x is pi over 3, I got 1.25. And when x is 5 pi over 3, I also got 1.25. So, what's the absolute maximum? Well, it's the largest output of the function, 1.25. And it doesn't ask for this, but I usually do it just because I like to be thorough. So pi over 3 and 5 pi over 3. Oops, that should say is 1.25. And the absolute minimum, how about that one? Well, what's the smallest value? Smallest value is -1, and that's at pi. So that's how you can use the extreme value theorem to find the highest and lowest points without looking at a graph. So if we looked at a graph, which I encourage you to do while we rest and consider, you'll notice that the graph has the lowest point at pi and the highest point at 1.25. So we're going to take a little bit of a break here. And it's going to be a break for questions as well as a break to recharge to get ready for what we're going to do next, because it's a bit of a shift. The next related thing we're going to talk about is a really large topic, and its size and interconnectedness to these topics, as well as the other topics we've studied before, is what makes this complicated. So it requires, on your part, a decent amount of study just to become familiar with the basic ideas. Especially with the restricted time we have with remote learning, it's not really going to be possible for me to spend as much time practicing and reviewing this type of thing as you might like. So I apologize, definitely not what I want either. So we'll make the best of it. And what we're looking at, again, big picture, is we want to be able to describe a function using its first derivative and or second derivative, and do it also vice versa. And we've done some of this already. So not everything we're going to look at is brand new. It's like, for example, we're going to be looking at functions the same 4 ways we've been looking at functions when we're trying to describe them. We're going to do it with reading, we're going to do it with writing, we're going to do it with tables and equations and also graphs. Those are all things we've done before. None of that part is new. We're also going to talk about when the function is increasing and decreasing. And again, this is not brand new. This is review. So we have studied this. Make sure you spell decreasing correctly though. But we're going to look at it in a slightly different fashion. Excuse me. Yeah, that's what I was talking about. So when it comes to an increasing function and a decreasing function, the first thing I want to look at with you is this slightly different idea than maybe what you're used to when it comes to increasing. So what I mean by that is there are a few different ways we could sketch, draw, think about, or look at the graph of an increasing function. So an increasing function could look like this, a nice straight line. It could look like this kind of a curve or some different version of that curve, maybe stretched out a little bit more, maybe really narrow. Could also be this type of a curve, again, stretched out differently. Maybe it's really steep and then slow, but it's increasing the whole way. And then we can mirror image those to do a decreasing function. So again, we've got a straight line decreasing, and that line can be pitched really, really shallow is the word that comes to mind, whatever the opposite of steep is, or really steep. And we can do the same thing with the curve. So it can be a pretty steep curve, or it can be a really slow decreasing curve. And then this type. So you may not have thought of a decreasing function in those fashion, or in those 3 different fashions, or an increasing function looking like those 3 fashions, but to boil it down in simplest terms, that's kind of what we can do. Okay, so we've talked about this, and this is review. G is a function that's increasing. The first derivative of G prime is positive. If G is a function that's decreasing, the first derivative of G prime, that's negative. All right, that's not new. We've also talked about the relationship between a function and its first derivative with critical values. Critical values of G means G prime is 0 or does not exist. And the reverse is true. If G prime is 0 or does not exist, G has a critical value. Likewise, a local maximum or minimum in G means that G prime changes from positive to negative or negative to positive in that order. And the reverse is true. If G prime of X changes sign from positive to negative, G of X has a local maximum. If g prime of x, the first derivative of g, changes from negative to positive, g of x has a local minimum. So those are the types of relationships we're talking about. These are things we've studied already. There's going to be additional relationships that we'll be looking at. But in order to do that, we have to learn a different piece of vocabulary. So let's build up for that. So make a couple of decent, well, just one right now. Make a decent sized curve that looks about like that. And then we're going to put several points on this curve. Okay. So you got that? Super. Now here are your directions. What I want you to do is I want you to draw the derivative at each of those points. So not the tangent line, just the slope of the tangent line at those points. So imagine you're just drawing in a really tiny point, or a really tiny line at that point, like this, little baby line at each one of those points. So like that, little baby lines, just the slope, that's all we're doing. Okay, that's all we're doing. We're drawing in little baby bits. Okay, so that's the slope of this function at a bunch of different points. Now there's a true statement that we can make about the slope of this function at all of those points. And that is the slope is decreasing. So if you look at all of the slopes at all of these points or any other point on this particular shape we've rendered, the slopes are decreasing. As x goes from left to right, the slope is decreasing. Okay, so that is a true statement that we can make. We're going to spend more time looking at that. But for right now, that's all we're going to say. Okay, so we're going to draw another curve. And we're going to do kind of the same thing. So the other curve is going to look like this. And we're going to draw in a few points. And we're just doing a few points because we can't do all of the points. We don't have infinite time here. And then at every one of these points, I want you to do the same thing. I want you to draw in the derivative, the slope. So just the slope, not a tangent line, just the slope of the line tangent, the derivative. That's all you're doing. So it's going to look like little baby bits of line again, right? It's like one right there, another one here, and one right there, and this one, and that one. Okay, so that's pretty much what your picture looked like, right? Little baby bits of lines, sure. Okay, we can make a true statement about every one of these slopes for this particular shape, and that is the slope well, now I've done it. Oh, sorry guys, you have to learn calculus from an idiot. Got these mixed up because I was too busy thinking about other things that don't matter right now. I apologize. So if I confused you when I said the slope is decreasing for that first shape, yeah, I confused myself too. So that slope is increasing. Similar to the slope for the other one is decreasing, not increasing. Yeah. And some of you are about to correct me. Anyway, so those are true statements that we can make. No, really, they're true this time, I promise. Okay. So what I want you to do is just spend a couple of minutes here thinking about why those are true. Like, what are you noticing about the slope that makes that true? And I'm going to pause the recording here. While you were talking, I don't know exactly what you all agreed on, but you maybe said some things like this. So for the first shape, we might have talked about how we have negative slopes, but those negative slopes get less negative, right? Here we have a really large magnitude negative number, like say -10. And then as we have points going this way, we have a more negative or a less negative slope, closer to 0. That means we're increasing. So we're increasing from very negative to less negative. And then we're increasing, going from less positive to more positive. And then over here, the reverse is true. We have very large positive slopes to less positive slopes to 0. And then after 0, we go to negative slopes. They're just a little bit negative, down to things that are really negative. So the values of the slope are increasing. The values of the slope are decreasing. Or expressed slightly differently, it's the derivative we're talking about. The same thing as saying the slope of a function is saying the derivative of that function. So the slope is increasing, the derivative is increasing. The slope is decreasing, the derivative is decreasing. But that's not all we're going to say here. We're going to introduce a new vocabulary term. That new vocabulary term is concavity. So that first picture we drew is an example of a function that I decided to name g of x. And for that function, g of x is called concave up. So when the slope is increasing, or the derivative of function is increasing, the first derivative of the function is increasing, the function is concave up. Or if we look at the graph of the function looks like that, we say the function is concave up. The graph of the function looks like this, we say the function is concave down. What does it mean to be concave down? Well, the slope of the function is decreasing, the derivative of the function is decreasing, but that's not all. First, some clarification. Saying the slope of g is increasing and saying the slope of g is decreasing does not mean g is increasing, does not mean g is decreasing. Before you start writing down and get buried in copying, look at the pictures with me. So we're going to look at this first one on the left. Notice how this is both a decreasing function and an increasing function. Concave up is both increasing and decreasing for the function. You cannot say g of x is concave up, so g of x is increasing. What's increasing is the slope or first derivative of g of x. Similarly, for the other one we drew, concave down. So this is the concave down shape. We cannot say g of x is decreasing. Look at it. G of x is increasing, then turns around and starts to decrease. You may not say for concave down, g of x is decreasing. It's the slope of g of x or g prime of x that's decreasing. This is what it means. Does not mean the function is increasing or decreasing, because it could be either or both. We don't know. All we know is that the slope is increasing for concave up and the slope is decreasing for concave up. I'm deliberately pausing, giving you a chance to write things down. So g of x concave up means g of x is increasing. It means g prime of x is increasing. Okay, we're going to do something very difficult. I want you to pretend that the function we're talking about temporarily is g prime. If I tell you that the function is increasing, what do you know about the first derivative of the function? If the function is increasing, the first derivative of the function is positive, correct? We're going to say that the first derivative is g prime. I'm sorry, we're going to say that the function is g prime. So what do we call the first derivative of g prime? G double prime. So this is also information we have when we know that g of x is concave up. So not only is g of x concave up, so it looks like this, the slope of g of x is increasing, g prime of x is increasing, g double prime is positive. The reason why g double prime is positive is because g double prime is the first derivative of g prime. So knowing g is increasing tells us information about g. I'm sorry, g is concave up, tells us information about g. We know what its shape is, concave up. Tells us information about g prime is increasing, and tells us about the second derivative of g also, namely g double prime is positive. And again, the reason why g double prime is positive is because g double prime is the first derivative of g prime. Okay. Draw your attention to concave down. G of x is concave down. The slope of g is decreasing. G prime is decreasing. Okay. Same type of mental gymnastics. Pretend that g prime is the first function. Okay, so g prime is not a derivative. What's the first derivative of g prime? First derivative of g prime is g double prime. The function is decreasing. The first derivative of the function is negative. But since we said g prime, the first derivative of g prime is g double prime. So knowing g of x is concave up or down tells us that the slope or g prime is decreasing and g double prime is negative. Now it fits here, but it doesn't fit here. Okay, so we actually know something else. And I want you to draw your attention briefly back to the pictures and notice something with me. Imagine if we were to extend our slopes into entire tangent lines. And then think about doing that at every one of these points that we did here. Okay. So imagine extending those lines. The function g being concave up will always be larger than the tangent line approximation. Since the function is larger than the tangent line approximation, we know that the tangent line will under approximate the value of the function. Another way we could say that, of course, is if the slope of g is increasing or g prime is increasing, the tangent line will under approximate the value of g. Or a third way we could say that is we could say g double prime of x is bigger than 0, which means g double prime of x is positive. The reverse is true when we are concave down. If you imagine extending every one of these tangent lines, every one of these tangent lines is above the function g. So the tangent line over approximates the value. This is similar to the idea that we looked at with the extreme value theorem, where we said all of these values are larger than every other value. So the tangent line over approximates the value of g when g is concave down, or when g prime is decreasing, or when g double prime is less than 0, which means g double prime is negative. All three of those things mean the same thing, and they have implications outside of just the shape. One of those implications goes back to tangent line approximations, which we studied earlier in the class. So make sure you remember this fact as well as these other facts. And I'm just about done spitting facts today. But there is another piece of vocabulary we need to learn in relation to this idea of concavity. And it's a point of inflection. So in the context of the graph of a function like we're learning, the point of inflection is the point on the graph of a function where the behavior of the function changes from either concave up to concave down or concave down to concave up. So the graph of G changes concavity. Doesn't matter if it's from concave up to concave down or concave down to concave up, the concavity changes. And points in G where that happens are called inflection points. So this has implications for the first derivative of G. So if G changes from concave up to concave down, how does the first derivative of G change? This has implications for the second derivative of G. So the function changes from concave up to concave down. How does the second derivative change? How does the first derivative change? We need to be thinking about all three of these ideas simultaneously. So go back to what we studied or just learned about. G is concave up. What do we know about the first derivative of G? First derivative of G is increasing. G is concave down. What do we know about the first derivative of G? First derivative of G is decreasing. So the graph of the first derivative changes from increasing to decreasing at a point where the graph of G prime changes from increasing to decreasing at a point where the graph of G changes from concave up to concave down. Similarly, concave down and then concave up, G prime, the first derivative of G, would be decreasing and then increasing. How about the second derivative? Well, the second derivative is the first derivative of the first derivative. So if the function is increasing, what's the derivative of the function? The derivative of the function is positive. The function is decreasing, the derivative of the function is negative. But remember, the function we're talking about is the first derivative. So this is actually the second derivative of G. Changes from positive to negative or negative to positive. So a point of inflection in G also has behavioral relationships in G prime and G double prime. I'm trying to repeat these in sequence, in context, to help you memorize these facts. And where did these facts come from? They came from the pictures that we studied. One more thought here, and we'll spend more time looking at this next week. So there is a pattern in the relationship between inflection points and the second derivative. And that pattern is when the second derivative does not exist or is zero, you're going to know to look for an inflection point in G. Crucial word here, may. So this is a little bit like looking at critical values of G in G prime to determine where potential relative extreme values are. But this is in the second derivative. All right. So to wrap up what we're doing here and give you some time to practice stuff and ask me things, I just want to draw a few pictures to give you an idea of what this concavity stuff looks like. Okay? So here's a function that you know and love, the arctangent function, the inverse of tangent function. So this function, when graphed, has two horizontal asymptotes at negative pi over 2 and positive pi over 2. Okay, this graph goes through 0, 0, and the graph has this shape from x equals 0 to infinity, and then this shape as x goes from negative infinity to 0. Okay, so look at that right there. The point I've marked 0, 0 is an inflection point. How do I know this? Well, because I know math, but how could you know this? So do you see the part from negative infinity to 0, that part right there? That part right there is concave up. So what we've done is we've taken concave up, which is like this, and we've gotten rid of that part of concave up, and we've gotten rid of the steep part of concave up, and we stretched this part out. Okay, see how that's concave up? After x equals 0, the graph is concave down. Why is it concave down? Well, concave down looks like this, right? That's concave down. Yeah, that's concave down. But we've gotten rid of this part, right? Gotten rid of that part. And then we kind of flattened and elongated this part out. Okay. One more quick pick, and then I'll turn you loose. I can't remember what the function looks like. No peeking. So here's this function. I'm not even going to bother to name it, but it's some kind of polynomial function. Okay, this function has several points of inflection. Can you find them? Well, let's find out together. So what's probably going to be easiest for you is recognizing the full shapes of concave up and concave down. So again, concave up is this shape. Concave down is this shape. So we can see a full concave up like right here, yes? That's fully concave up, okay? And over here, that's fully concave down. So that means some point in here it may not be exactly where I've drawn it. It might be further down here, it might be further up here, but somewhere that's got to happen, yes? We got to change from concave up to concave down, okay? So where are the other inflection points? Hint, there's two more. Okay, here they are. There's one somewhere right about there. And there's one somewhere right about there. So again, they may not be exactly there, but they're somewhere around there. So what I want you thinking about is how the graph is concave up. It's decreasing and it's concave up. And then somewhere in here, the graph changes to this part right here. So the graph starts to decrease somewhere in here, right? And as it starts to decrease, it's concave down. And then we know the graph goes into concave up. So it's decreasing and then increasing, but it's concave up, and then it keeps increasing, and somewhere it changes into concave down. So if we were to do the same kind of slope analysis, which we're not, because that's going to take a really long time, but we could say how all of these slopes are very, very negative, and then they become less negative approaching zero, so the slope is increasing. And then starting here, slope is zero, these slopes are negative again, they get more and more negative as you come closer to here, and then less and less negative to zero, and then more and more positive, and then less positive, and then approaching zero again. The slope is decreasing again all the way to infinity. Promise I'm done. So we're going to be spending more time talking about those types of things moving ahead.